Yeah, wonderful. Thank you all so much for joining us for this February 2023 edition of Link Tech Talks. And so today we will hear about the TOM Toolkit and SkyPortal. And first we will start with SkyPortal, and this will be presented by Joshua Bloom. So he did his undergrad education at Harvard and Cambridge, and then continued to do his PhD at Caltech. His astronomy research focuses on gamma ray bursts and other astrophysical transits, such as supernova and tidal disruption events. Josh is the chair of astronomy department professor at University of California, Berkeley, and was a co-chair of the Transit and Variable Star group. At one point, he left academia for 4 years to start a company, but now he's back, and he will tell us about the SkyPortal. So we will have 2 talks. I suggest it will be around 20 minutes each, and let's have a discussion at the end. If you have short clarifying questions, we can have it at the end of the talks, but put your questions in the Slack or here or unmute at the end, and I hope we have a good discussion after the end of the both talks. Okay, take it away, Josh.
Thank you very much. It's really nice to be here and be back with this group after so many years. You're looking at a screenshot of our dashboard of SkyPortal, which is what I'll be discussing today. But just to orient you a little bit of what our users see on a daily basis, I just wanted you to have a view of that. I'll come back to some of this later on. So I'll be talking about SkyPortal, which is an astronomical interaction and coordination platform that we've been building for the last 6 years. There's a link there, actually 2 links. The second one is for a series of YouTube channels that we've been building. I'm also joined here by my colleague, Michael Coughlin, who will be helping me in some of our discussions at the end of the talk, and can help fill in any of the details, especially on the multi-messenger astrophysics work that we've been doing within SkyPortal. So I'm going to flash up now a slide with a lot of words on it, and then I will read what's on the left-hand side, which is sort of the most concise way that we describe what it is that we're doing, and then go into some of the highlights. So SkyPortal is a portal utilizing secure modern web technologies, scaling effectively, and is highly customizable, not highly customizable, and extensible to various astronomy workflows related to ZTF, LSST, LS4, and other surveys. We see it as a single source of truth marshal for transient, variable, and solar system science cases. It facilitates follow-up observation management, including robotic and also classical facilities. So I know that's a lot. Some of the finer points to note about what this system is first and foremost, it's open source. So anyone can use it, modify it, distribute it. We've had a number of groups outside of our own that have started using it for their own science purpose. And one of the fundamental ways to think about SkyPortal in the large landscape of the different code bases that are out there is that we don't see it as something that we have to centrally manage. We want people to be changing it and making it their own, but we feel like we've built some really good bones to do a lot of different diverse types of workflows. It's an API first system, so pretty much anything one can do on the front end, you can do as a machine on the back end. Extensible and scalable by design, so it's sort of all run and orchestrated within a sort of Kubernetes paradigm, so we can spin up larger and larger systems as we need to for a larger and larger load. One of the things that I wasn't expecting to do when we started off on this project is to build in fine-grained access control. And what that means is that essentially every data point has a notion of who can see that data. When we think about open source software, it's not so hard to think about open science. And the nominal idea would be all data that everyone can see. But as it turns out, life is a little bit more messy, and we were asked by our users to be able to have that kind of control. I'll say a little bit more about that later on. Interacts with the kinds of things that we all do in our daily lives, like with Slack and SMS messaging. We have a set of rich visualization capabilities. And some of the new things that I'll talk about towards the end of the talk is our ability to do multi-messenger astrophysics planning for follow-up, to trigger wide field imagers, to take data in a way that's optimized, for instance, for kilonova discovery, and then take the results of all those observations and all the candidates and filter that back in to potentially refine the planning of those discovery facilities. We've also recently introduced the ability to do third-party analysis at the individual source level, which can be triggered either through the front end or the back end. And that allows all the data that we have within SkyPortal about a given object to be packaged, sent over to some third-party system through authentication, and have the results of what could be a very long-running analysis from seconds to minutes to potentially days to come back in and have SkyPortal serve as that single source of truth for that analysis. We have the notion of distributed computing. We are doing a deployment in the cloud with Kubernetes, but you can also use Docker Compose. And one of the things that I'll harp on a little bit with the lessons learned is this notion that we're trying to be as well tested with extensive documentation as possible. So as I said, we are API first, and one of the sharp elbows that I instituted within this project early on is that we should be able to do everything programmatically, that you could use this in a sort of headless way if you wanted to, and have various different robots using their tokens, interacting with just about anything you could possibly want to do within these systems. So for those that are interested in seeing that documentation, there's a link there below. And just to put SkyPortal in context, how we sort of fit into the universe of observing and where that fits in more broadly, we've got a number of telescopes that are acquiring data. They're doing their own data reductions. They're finding, in the case of time domain astrophysics, candidates. And I've thrown up a couple of different logos here. There's a group within MIT TESS that are using their own SkyPortal instance to save and visualize and then interact over light curves of TESS objects. But the DESI collaboration is using not the time series aspect so much of what SkyPortal presents, but more about the spectroscopic capability. And they're doing this in the context of time domain spectra. We've been working very closely with the ZTF collaboration, which I'll say a little bit more about in just a minute. And we will be serving as the marshal for the Lucia Schmidt Southern Survey, LS4, in the future. So these candidates are found, they are broadcast through Kafka or other streams to brokers. There's a broker that we have a very close connection with called Kowalski, visualized as a penguin here, but other people have been building brokers that can listen to Kafka streams and then speak our API language to essentially upload data into our system via the API, so that there are candidates that then users can see through the front end. They can get notifications on if they match certain filters, and the users can, of course, interact back. And then SkyPortal, as I said before, also can interact with these third-party analysis tools, which I'll say more about later. And then as part of the interaction over individual sources, users can request follow-up time on robotic and Q-scheduled observatories. And the results of that work can be pushed back into SkyPortal again, so it becomes a single source of truth and record for an entire team working on a large number of different projects together. And so those of you who've followed this world a little bit may have heard of something called Fritz, which is the ZTF marshal, and everything inside of this orange line here is what Fritz is. So it is ZTF pushing data to Kowalski, and Kowalski is doing the filtering by different groups. And when it finds something that matches a filter, it pushes that data into SkyPortal. I won't go into great detail about our stack. I know that's of interest to this group, and I'm happy to answer questions towards the end about it. But it's, in some sense, a fairly vanilla stack in a modern web sense. So it's a React and Redux front end. It's a sort of Python middleware with a Tornado a way of thinking about doing web interactions. It's all backed by modern Postgres 14. Although in principle, because we've written everything in using SQL Alchemy as our ORM, one in principle could pull that out and have a different database system in the back. There may be a couple issues on the outskirts, but that should probably work. And then things like Supervisor D for microservice management. Our deployment stack is Kubernetes on the Google Compute platform, and Google Compute manages our database for us, which is really wonderful because then we don't have to deal with updates and backups. And when things go bad, we can very quickly get back up and running with our database. GitHub Actions are used for CI/CD, and we have now over 1,000 unit and integration tests. So every time when we deploy, we sort of know what we're getting ourselves into. Every time when we merge a PR, we know what we're getting ourselves into. And we have a very simple system of, a separate staging that has sort of smaller disks and is not as a large set of VMs. And we push to that and we make sure all the new functionality works. And that's sort of our last moment before we then push to production. And we have, Slack and SMS monitoring if things go horribly wrong. Our people stack, we have a really wonderful, diverse team that's some of us have been around since the beginning, and then we have new people coming in and out all the time. And it's been absolutely wonderful to see people grow in their software skills and building this system as we move through it. So we have a fairly rigid set of requirements around how pull requests are reviewed and how they go in. We have our users tell us about things that they want or things that have gone wrong via issues. And we have regular meetings and we do weekly deploys. That's sort of the cadence that we've gotten ourselves into. So this is the dashboard. I showed this before. It's configurable, so people can show different widgets as they want to, and each one of these widgets are themselves configurable. Notions of users and groups. So within SkyPortal, there can be different groups. People can belong to these different groups, and they can be managed by group managers. People can request admission to these different groups. And the way to think about a group in our world is that a group is a single or a set of very similar-minded filters on incoming data streams. So the red transients group is a group that's interested in red transients, and they've built a set of filters within Kowalski that allows us to push all of the data that's then associated with that group. Groups have notions of belonging to different data streams. So if there is a proprietary data stream, which we have within the ZTF collaboration, different members of different groups would get access to that data stream via their membership in those groups. One of the most important things that we've done, and this is sort of building off the heritage from PTF, is build the capability of doing scanning, because oftentimes in the time domain, humans are required to be in the loop to go through and look at candidates by eye just to make sure that they aren't bogus or that they actually match the kind of expectations for those filters. And so one of the early capabilities we built was the ability to go through and look at different objects, save them to that group or save them to multiple groups so multiple groups could see those objects. This is something that somebody does every day. Multiple people do this every day for their own group projects at the end of the night. We also, as I mentioned before, have this notion of follow-up triggering, and we have a number of telescopes that we've already started communicating with, listed on the left-hand side. Some of these are Q-scheduled, some of these are robotic. Every telescope can have a series of allocations, and people can make requests to a specific allocation with a certain set of priorities, with certain start and end dates, to do follow-up on some of the objects that they're interested in. Those get pushed out if they get observed. In many cases, they get pushed back into us, and so the data can be observed and uploaded programmatically, and then they get charged essentially against this notion of an allocation. As I mentioned, also, we have a number of different analysis tools within the platform that allow people to do their science. So one can define ahead of time a set of analyses tools. We have a couple of those as exemplars. A supernova analysis tool, which is essentially a wraparound SN Cosmo, a kilonova fitter, GRB afterglow fitter, and these serve as microservices within the SkyPortal ecosystem. And when somebody wants an analysis using one of these services, they essentially push a button on the front end or make an API call, and those are then done, and the data is saved. So we get posteriors on parameters. We get plots and things that are made by these third-party analysis tools. We also have an in-browser interactive periodogram analysis. So if you've got a variable star and it doesn't yet have a known period, you can go in by hand and run Lomsgargle periodograms and actually interact with the system and save those periods. And one of the things that's also really interesting in terms of the third-party analysis that we don't actually supply is that there is a group within the ZTF collaboration that is looking at bright candidates, which are saved automatically because they have such a high probability score of being real. Then they're scored using a deep learning system called SN1A score that Michael is part of. And if it has a high enough score, spectra are taken with the SEDM machine autonomously. It's then typed autonomously and then pushed back into SkyPortal and then pushed back to TNS. So regularly we are discovering, and then following up and classifying supernovae every single night without any humans in the loop. As I mentioned at the top, we have a number of training videos for people who are onboarding to learn about all the different capabilities. And we're working at scale. So this is a little bit outdated, it's a couple of months outdated at this point. But we're pushing into the 500 million numbers of photometry points. We're over 6 million candidates, over 2 million sources. And the thing I think we're most proud of is we have hundreds of users who are interacting with our system, not all on a daily basis, but many. So this is becoming a pretty beefy system, and people are obviously finding value from it. Last couple slides, just talk about the O4 workflow, really just to point out that we've been spending a lot of our time trying to get ready for this, so that when there is a discovery from Fermi and or the LIGO Virgo Kagra collaboration, we know about those localizations on the sky. We have efficient ways of tiling that, and then we're talking to individual telescopes, and then we are able to push out some of our discoveries external to SkyPortal for others to be able to follow up. So we can define default observing plans based on different types of triggers. So the one on the left is related to a Fermi GBM trigger, and there's requirements that it would be less than, say, 500 square degrees. And then we have different notions of how to actually do the slewing, do the tiling, and more or less we're trying to figure out a way so that people can define a follow-up program for the science that they're interested in. And then within SkyPortal, be able to figure out what their efficiencies might be by looking at a number of fake injections and figuring out how many of those they would actually wind up seeing with that specific plan. So some of the key features is that we've been working with Leo Singer in particular on doing very fast and efficient galaxy cross matches using heel picks within SQL Alchemy, trying to improve our telescope triggering interfaces, and working on our observing plans, not just for an individual telescope, but potentially multiple telescopes, so we can federate some of the work that's needed. And again, we want to be the one-stop shop for light curves, so that we can not just do the analysis as the data comes in, but after the fact, because we know what our different limits were, be able to get some realistic parameter constraints. As I said, we've got a really wonderful a developer group that's some of us have been around for a while, and some have left us. We have alumni that we're very proud of that learned quite a lot, have gone off to greener pastures, and I feel like we've built something not just of value to others, but it's been of value to us as a team. And I'll just end, I guess, with some lessons learned. And many of you have been in the software world, know a lot of these already. It is absolutely critical to build diverse teams on many axes. You need front-end engineers, back-end engineers, people who care about security, but also people that come from different backgrounds who bring different sets of talents and views into a large-scale project like this. Another thing is, no matter what, you're not testing your code enough. We think we test our code a lot, but we know we're not doing as well as we could. Disaster strikes even when you change a couple of lines and you think everything looks good on your laptop. When you push to production, things can go horribly wrong, and they have. Database migrations need to be tested because if you are building a database and you're constantly adapting as you're adding, you could also be subtracting. And being able to go both forward as you add new columns or new tables, and also being able to go the other way as you remove them is critical. I'd say another thing is prioritization is hard. We don't have product managers. So we have lots of users, and oftentimes the squeaky wheels tend to get most of the attention. And so keeping a clear-eye view about what your system does and what it doesn't is really important. I wouldn't say we've been 100% great at this, but oftentimes we need to sort of make some hard choices and say no. And then last, you all know this already, production is really hard. And anyone that's been following the news on pretty much a daily basis, people working at Google and Microsoft make mistakes that have $100 billion implications because production is hard. And it's really hard to do this when you're working on a bare bones with a small team. I guess the other big thing is we've been really building this huge plane while we've been flying it, and we're trying to squash bugs and build new things, both big and small, and there are huge challenges around that. But to be honest, I wouldn't say we'd want it any other way. This is the way in which I think you can build a great system that people use is not by building it in the abstract and then delivering it, but by building something that's an MVP that has some of what people want, gets them going, and they say, I'd really like this. And then with those sharp elbows, wearing your product management hat, you can start building roadmaps that start drawing people in and making the system better. So I'll end with just saying, anyone that finds this of interest, we're always looking to engage with new people. We've got really a nice onboarding capability, and we've got needs across the stack. So please, even if you don't interact with us, contribute code, make pull requests, and we're happy to see what people do with SkyPortal. So I'll end there.
Okay, wonderful, Josh. Thank you. Thank you so much. Okay, I don't see particular questions, or at least short ones in the Slack channel and Slack. So I think we will continue to Rachel, and then we will at the ends. I have, of course, some questions, and we have some coming in. Excellent, great. Okay, so Rachel, maybe if you could share your slides.
Okay.
Okay, and while you're getting ready, I will just say, so next talk will be given by Rachel Street. She studied at University of Birmingham in England, and then she did her PhD at University of St Andrews in Scotland, where she was searching for transiting exoplanets. And then she continued her tour of the Isles by going to Queen's University in Belfast, studied some microlensing, then she joined Les Courbes Observatory, where she founded the microlensing research group, because she's contributing to the preparation of both Nancy Grace Roman Space Telescope and the LSST. Until recently, she was also a co-chair of the Transit Variable Science collaboration, and she will tell us about the TOM Toolkit project.
So thank you very much, Nevin. Can you hear me? Okay.
Yes, I think so, yes.
Great. Okay. Well, hello, everybody. I'm excited to this opportunity to tell you about the TOM Toolkit and some of the new features that our team have been working on. But first, allow me to acknowledge the team behind this project, especially LCO software engineers William Lindstrom, Joy Chatelain, and John Nation, who work in collaboration with our science team to develop this package. So Rubin and other discovery engines will bring an enormous wealth of discoveries, but survey alerts are not the same thing as physical understanding. So the challenge is going to be to synthesize all of the available information in real time so that we can identify the most important targets. Now, Rubin data alone may not be enough to characterize those targets. So for that reason, it's often important for us to decide in real time whether or not to select an alert, and if so, what observations to make. And of course, the challenge with Rubin is that it will produce a massive amount of data. So synthesizing information on targets of interest is going to involve managing all of that data, bringing together catalog information, and if you do need follow-up observations, managing a very large-scale follow-up program over a long period of time. And this is where software tools can really help. Target and Observation Manager Systems, or TOMs, are software tools that are designed to streamline that whole workflow and reduce the overall human workload. They make the whole process of synthesizing information and implementing a follow-up program so much more efficient. The TOM systems take advantage of the programmatically accessible alert streams, brokers, data archives, telescopes, and they retrieve information relevant to a given target and display it in one place for evaluation. TOMs are also a platform for communication. The humans involved in a project are often geographically distributed, so by making these available platforms online means everybody can access the team's science data, post comments, coordinate follow-up efforts and publications. The TOM system that you can see in this display is developed by a team in Poland based on the TOM Toolkit, and it serves team members across Europe, the US, and Asia. They can easily be deployed into a cloud-based hosting system, and it's very easy to make them Dockerized and available worldwide very robustly. But one of the most powerful features of a TOM system is that they can directly submit requests to observations to many telescope facilities. And that really streamlines the whole process of a follow-up program. And it means you can respond to alert very effectively, sometimes without even human intervention. So to demonstrate a TOM system in action, I'd like to share an overview of the new Supernova Exchange. This system serves over 200 members of the Global Supernova Project worldwide. So from the target page, you can search for targets of interest by name, coordinates, or simply by clicking on the list of latest available targets. This displays a target page which brings together all of the available information on this object so that you can assess it at a glance. The first panel gives you the catalog imaging, which you explore through an interactive Aladdin viewer. And you can also see next to that a time series of follow-up observations. Scrolling down, we can see the follow-up reduced data products, the photometry and the spectroscopy. On the left, you can see a list of institutions who have access to data on this event. Big collaborations often have rules governing who has the right to see specific data products, and the TOM administrator has the ability to manage permissions for each user and group. In the top panel, you can see a latest comments box. This allows team members to record their comments, to chat and coordinate their work. And team members can upload the data products from their own analysis to share them with the rest of the team using this interface. The toolkit also provides API hooks, so you can programmably upload from, for example, a data pipeline. If you do decide more observations are required, users can plan observations and request them from a wide range of instruments just by filling out this online form. On the left, we have photometry, and on the right, we have spectroscopy. The toolkit also supports customizable observing strategies, such as predefined functions that tell a TOM what to do if a target meets certain criteria. In addition to LCO, the SNEX2 team also make use of the Gemini telescopes, and users can submit requests for the Gemini instruments just as easily. The toolkit supports several other facilities as well. These are just the ones in use by this particular team. Now, say, for example, we have requested imaging of a supernova to be made every few days. A large program may have many targets, and it's only too easy to lose track of a target that should be reobserved. So the toolkit provides cadence request functions that monitor whether or not the requested observations have been completed successfully, and can automatically either resubmit or cancel the program if it's decided if the observations have not progressed as intended. So TOM systems have proven to be extremely powerful tools for many different groups, but developing one from scratch requires substantial development effort. So the goal of the TOM Toolkit was to provide an open source and easy to use package that anyone can take and use to run a TOM system for their own science, which is maintained to professional standards by LCO's own software engineers. We recognize that different science teams have, of course, different requirements. So rather than build a single monolithic system, the toolkit provides very functional system out of the box, which users are then encouraged to customize. The out-of-the-box system includes all of the core features, and we provide extensive documentation and training materials to help you to add features, customize the displays, add interfaces to new services such as your own telescopes, and to, importantly, add interfaces to your own user-developed analysis software. The TOM Toolkit provides tools to receive alerts from the Rubin alert brokers, including Antares, Alerce, Laser, Fink, as well as a range of other services such as Scout. Users can design queries to select targets of interest to them, and then store those queries for reference so that they can be run repeatedly. The broker typically returns a list of objects matching the query, and the user can then select which targets they wish to ingest into their TOM for further study. You can also add and customize the parameters that are stored with any particular target. Now, users can do this through the broker interface, the browser interface, if you prefer, as you see on screen, or you can automate this entire workflow so that the TOM harvests automatically on your targets of interest automatically. And you can also add information to targets by querying catalogs and online data archives such as Simbad, NED, etc. Oops, move on. Yeah, there we go. So in addition to the core toolkit, we also have a range of plugin modules with specialized features designed to support particular science cases or services, such as telescopes or certain alert brokers. These plugins are deliberately designed to be optional so that users only need to install those functions that they need for their science. Additional software features always bring additional dependencies, and that can lead to a maintenance headache. So the way we've structured it means that we keep the package as user-friendly as possible. So I'd like to talk about some of the new plugins we've developed that are particularly relevant for Rubin science and also multi-messenger astrophysics during the upcoming 04 run of the LIGO Virgo Kagra detectors. The first is the new TOM Alert Streams module, which provides a TOM app which will listen to a Kafka stream of the user's choice. New Kafka services are coming online, including the GCN Classic over Kafka service, as well as, of course, the alert brokers developed for Rubin. And it's straightforward to configure your TOM to listen to any alert stream that you prefer. We've also added a TOM classifications module, thanks to some excellent work by Brendan Mills from UCSB. Their different alert brokers, of course, are providing independent assessments of the alerts coming from Rubin and other surveys. And by comparing the classifications from different alert brokers, we can build confidence in our identification of targets of interest. Brendan also developed these excellent interactive charts so that you can easily visualize the alert information coming from different brokers. Of course, the next run of the gravitational wave detectors is scheduled to start in May. And this is a great example of a large community following up discoveries from a major survey in real time. So the technologies involved overlap with those that will be used for Rubin. There are many teams across the world that will be expected to follow the discovery alerts, and they'll be observing them with telescopes both on the ground and in space, and combining information from all wavelengths and messengers. The initial localization of a gravitational wave alert can, of course, span hundreds of degrees. So the race is then on to pinpoint the origin of the signal before any electromagnetic counterpart fades. Many facilities have to target specific regions around known galaxies, while others can target the entire localization region. So there are multiple candidate pointings associated with the same non-localized event. So we've developed a new TOM module to support the follow-up of gravitational wave events. This plugin allows you to create an index of the events of interest, which also links out to direct links to the other services providing relevant information. This one takes you to the Treasure Map service, for example, where you can see other observatories observing that region. And you can also go directly to the GraceDB entry for the event. But if we click back on the TOM's own page for this event, you can see that it's harvested the important information and visualizations from GraceDB, and it provides an interactive table of the GCN notices, ATALs, and other relevant messages about this event coming from other observers. Sharing messages with updates in real time helps the observers to coordinate their efforts with the other teams that are observing the same event. Scrolling down, we can also see the list of targets that are associated with this localization region. These are the targets that this particular team have decided to observe relevant to their follow-up strategy. Targets can be added to the active list or retired if observations fail to find a counterpart. And by clicking on the target will take you to the TOM's own target page for the object, where you can request suitable observations. Now, previous runs of the LIGO Virgo detectors demonstrated the need for coordination between the follow-up teams. And to show why, here is a very short time lapse showing the telescope pointings that covered the localization region of one gravitational wave detection. As you can see, quite a lot of people observed that in just a few days. This can lead to a lot of duplication and a lot of wasted effort and a lot of unnecessary disruption to other observing programs. So there's been quite a lot of efforts within the multi-messenger community to improve the coordination between teams. The toolkit already supports several existing platforms for the rapid reporting of results, including the new GCN over Kafka service. There's also a new Kafka-based messaging system called Hopscotch, which was developed with the goal of increasing the amount of information that's available in a machine-readable format, which makes it much easier to integrate it with programmatic services. The system's integrated with the Keycloak identity and access management system that's been formally adopted by the LIGO collaboration. LCO has recently developed the Hermes service, which is based on Hopscotch. The Hermes portal allows you to post different types of astronomical data, which is then converted to JSON format and disseminated via a Kafka topic. It also offers an API so that you can post messages directly from software such as a TOM system. So a new plugin for the TOM allows a user to select which data they wish to share from a table shown on the screen, and to which Kafka topic they would like to send it just by clicking a button. The new TOM plugin for Hermes supports Keycloak so that the TOM can seamlessly interact, and the whole workflow can be automated if that's what the TOM user prefers. So here's a demo of how this sharing works in practice. First, we see a TOM system run by Team 1, and we're going to show the data that they've acquired on a particular target. As you can see, they've acquired some photometry and spectroscopy. Now we go to TOM2. This is run by a different team, and as you can see, they don't yet have data for this object. Now, Team 1 says they're happy to share their photometry, and so they select all of the data points they want to share from this table, select the Kafka topic, and then hit share with Hermes. Now we can see that particular Kafka topic on Hermes, and we can see the post from Team 1 and the data that has been sent along with it. Now, if we go back to Team 2, in order to receive the updates from other observers, this team has subscribed to that same Kafka topic. So they receive messages that are posted through Hermes, and the TOM ingests the associated data. So if we now reload that photometry data page, we can see that the data from Team 1 has arrived. Oops. So teams in the community now have mechanisms to share information between groups who may develop TOM systems, even if those TOM systems have been built with entirely different code bases. And that allows the teams to better coordinate follow-up, especially for rapidly evolving events. In addition to sharing data via Hermes and Kafka streams, we're also working on mechanisms for the TOM Toolkit to TOMs based on the TOM Toolkit to share data directly. So I hope I've given you an overview to the TOM Toolkit and a quick insight into some of the new tools that are available for Rubin Followup and also for the 04 run. There's a lot that I haven't had time to go into that is in our development plan for the near future. We are in the process of making it possible to request observations from a much wider range of telescopes, including supporting telescope operators who have contributed time through the Rubin in-kind process. We are working with developers of the Rubin alert brokers to make sure that our interfaces to their services are kept up to date to support their latest functionality. And we're working with Desk on some features they requested for their TOM system for their science. And I'd like to end by saying that we place a really strong emphasis on supporting users of the toolkit to do their science. So in addition to our online documentation, we plan to run workshops at the upcoming winter AAS meetings, and we encourage research teams to get in touch with our developers if there's functionality that you need and we can provide. So I'll stop there, and thanks very much.
Wonderful. Excellent. Thank you so much. Great. So we have around 15 minutes for discussion. So either raise your hand in the Zoom, or if you put a question in the Slack channel or in the chat, then we will read it out. And while we are waiting for that, I wanted to ask you, for instance, Rachel, so you were saying that you basically taking different brokers when they are classifying, you somehow, and I could imagine that's like herding cats, you take these 8 classifications and somehow you try to get all this information together. How does that work? And I assume different brokers have different classes. You know, that sounds quite...
Yeah, so yeah. My student Brendan has spent a very interesting project looking at that and actually comparing the classifications for a set of alerts that were classified from ZTF, but classified by 3 different broker providers. And the level of agreement he found was actually reassuringly high, sort of the order of 70% where they more or less agreed on what the classification was. But in a substantial fraction of cases, they actually didn't agree. And he developed the visualizations that I showed on my slide, which really helped to highlight not just where the disagreement was and whether they were consistent on a given event, but also in some cases you can provide the categorization, and some brokers provide information on the probability of classification of different types of alert. And he was able to come up with some really cool visualizations that show you at a glance whether or not this target is really what you think it is.
Thank you. Okay, maybe Monica.
Yeah, thanks. Very nice talk, Rachel. A quick question. Is there a plan to incentivize authors for posting their Followup results on Hermes?
Incentivize them? In what sense?
So like, for instance, if people post it on ADL or TNS, you have those records in ADS. It's searchable, right? It's indexed there. So
yeah, so Hermes is searchable, and it's a single shop that actually combines information coming from various disseminators of information in a machine-readable way. So it is searchable. It will have a referenceable post. So you get the DOI, you get the credit for posting your information, but it becomes functional to users in the way that's more usable for programmatic systems, and it's all in one place in a very simple system to use.
I see. Thank you.
Okay, Colin. I am familiar with the setup. Yeah, laptop is maybe better, Colin.
I can't hear you very clearly, Colin. I don't know if anyone else can.
Sorry, the microphone's not working. Just this quick question of each platform might be able to say something about solar system science. I saw Josh had a front on the slide saying something about that, and Rachel, I know that you're also involved in that. I'm just curious, like, how moving targets are handled, and I saw Lindstrom brokers in there mentioned. If you could just say something about that for each one, I'd appreciate hearing that. Thanks.
Yes, we certainly support sidereal and non-sidereal targets. So we have full support for moving objects in the TOM Toolkit. In fact, one of our lead developers, Joey Chatelain, is a solar system scientist. So he is very alert to making sure that all of our functionality is applicable to moving targets. We also support queries to JPL Horizons, Scouts, and other services designed specifically for moving objects.
So we have the notion of sources, and those are could be fixed on the sky or maybe moving. We don't have the ephemeride of individual sources that are moving front and center, but they can be saved by source. And we also don't have the ability to do a query, say, in Arian Deck at a certain time and be able to get all the sources that are within within that box that have been moving. I can see exactly how we could do that if there's interest. So we could talk offline about adding that functionality. But I guess the other thing is we are able to query the Minor Planet Center and other systems, so that when we have a source, one of the things that somebody can check is whether it overlaps with the position that would be calculated for that time of observation.
What I was wondering, Josh, I remember, and going back to Monica's question in the chat, you were showing that you have like hundreds of users now and so many alerts, but when LSST comes, maybe wrong, you know, I expect much larger scale of requests, and like, is that, do you envisage some sort of problems? Because a lot of these are like, I find a single object, I manually follow up. Do you see that kind of continuing?
Yeah, so you know, we're not positioning ourselves to be the place where everyone would go to do this work for LSST, in part because there is an expense to managing these systems and running them computationally in the cloud or locally. So people could do that, and our expectation is that people will download SkyPortal, run it as an app on one of their machines or in the cloud for their collaboration. And somebody, you know, it could be even us, gets funded at a larger scale that would allow us to serve that to a much larger group. And then there, the permissioning on data rights becomes even more important than it does now. We don't have an upper limit on the number of users, on the number of groups. The amount of data associated with that is trivial compared to the raw data that's coming in. Where it would have an impact is on the number of concurrent database interactions. And that I can see at some scale becoming a big enough issue that we may have to do some re-architecting, but doubling, tripling, even 10xing the number of concurrent users, I don't think would be too taxing because we would be able to scale up to larger systems. Beyond that, we may have to do some re-architecting if that's where people are heading with it.
Okay, Sam.
Hi, yeah, great talk from both of y'all. I was wondering, both of y'all offer with your services potential to trigger observations with follow-up facilities. As we know, a lot of astronomical observatories don't have API hooks yet, or they're developing at the same time. So how easy would it be to incorporate a new observatory or a new instrument to be triggered with both of your services?
I guess I can take that first. It's certainly not trivial, but we do have a pathway to that. And I posted in the chat a link to the code where people have added the hooks into various different telescopes. I think we're at, something like 24 now. So if there is a very straightforward API, then you can do that all through the front end. If there isn't, then you need to build the specific dance, and express that in code, and then make a PR back to SkyPortal, and we just kind of add that in. Maybe I can ask Michael, put you on the spot. You've done a few of these now where you've created that interaction. Can you say a little bit about the time that it takes to do that?
Sure. Can folks hear me?
Yeah.
Okay. Yeah, so it of course depends on the complexity of the API. Experience has been that these days it's, maybe an hour of work depending on how complex the API is. And the other thing that's become quite popular because, APIs aren't obvious to all users, we have folks who quote unquote trigger through Slack or email, right? Through the exact same process as you would CTF or one of the other, let's say, queue-driven schedulers. And so it's actually a lot of work has gone into it, but a lot of people are using it successfully now. So, and just like Rachel said, we're always happy to help.
So to answer from the TOM Toolkit side, we have documentation available from our website on how to write a facility API interface for the TOM Toolkit for any telescope. And in fact, we've had a particular TOM team working in Europe who have managed to have observers involved from, I forget how many, dozens of telescopes they're using for their TOM. So it's certainly easily possible. From the side, it does need an API, as Josh noted, on the telescope side to receive and send information regarding observing requests, telescope status, etc. So some facilities have that API in their own system, and we work with the telescope operators to build a plugin that will talk to their existing system. LCO has also made available the Open Observatory Control System package, which is available for telescope operators. It's an open source package which they can download, and it actually provides those APIs. So telescope operators are welcome to use that package, and it comes ready built with facilities that will talk to the TOM Toolkit. So the end-to-end system is easy to build. And we're very happy to work with any team or telescope operator that wants to implement that. Come talk to us. We're very happy to help.
Okay, great.
Thanks.
If there is maybe one more question, this would be your chance. Okay, but if not, last chance? No. Okay, but if not, I would like to thank Josh and Rachel again. And the next talk will be March 9th. So it's exactly 1 month. And it will be, we are still a little bit deciding exactly, but it will be folks from Space Telescope in Baltimore. They will show us Jupyter notebooks, how they're serving them, some nice examples with the telescopes that they are running, and overview of the mass system that many of you must be familiar with. And then the April slot is at the moment free. So I would be very happy if you have a good software proposal connected with LSST Sans, or your colleague has, if you send me and Colin an email, we will definitely consider it. Okay, thank you, Josh. Thank you, Rachel, so much. Okay, thank you.
Thank you. Have a good one.